It's one of those questions that refuses to go away. Does the universe spin? Everything else in the cosmos does. Planets rotate, stars whirl, galaxies twirl in spirals that stretch across millions of light years. Even black holes, the ultimate sinks of space-time, spin with such force that they drag space itself around them. So it's natural to wonder, if everything in the universe spins, why not the universe itself? For centuries, thinkers have entertained the possibility. Newton considered it. Einstein did too. Mathematician Kurt Gödel even discovered a theoretical solution to Einstein's equations that described a rotating universe. But for all that, there's never been solid evidence. No measurement, no observation, no telltale sign in the night sky. Until recently, it remained a curious but unverified idea. But now, an intriguing new paper by Szigeti and collaborators has reopened the discussion. And they're not just asking if the universe spins, they're suggesting that it might actually solve one of the greatest current mysteries in cosmology, the Hubble Tension. At the heart of the Hubble Tension lies a seemingly simple question. How fast is the universe expanding right now? Known as the Hubble constant, this value should, in theory, be straightforward to measure. But there's a problem. Two trusted methods give two very different answers. The first approach involves observing nearby galaxies, measuring their distances, and the speed at which they're receding from us. This yields a value of about 74 kilometers per second per megaparsec. The second method looks at the ancient light from the cosmic microwave background, the afterglow of the Big Bang, and uses a cosmological model to predict how fast the universe should be expanding today. This method gives a lower number, about 67. This discrepancy isn't just a rounding error. It's a growing rift that has persisted despite increasingly precise measurements. If both methods are sound, something must be wrong. Either our observations of nearby galaxies are flawed, or our model of the universe itself is incomplete, and this is where the idea of a spinning universe steps in. Szigeti and colleagues proposed a novel approach. What if we treated the universe not as a static, symmetric field, but as a rotating fluid? This seemingly simple shift introduces a host of fascinating consequences. In particular, it invokes the concept of frame dragging, a prediction from Einstein's theory of general relativity. When massive objects spin, they don't just curve space-time, they twist it. Like stirring a spoon in honey, the rotation pulls the very fabric of the universe along with it. This isn't just theoretical. We've observed frame dragging in binary systems where a white dwarf and a pulsar orbit each other. The pulses from the pulsar arrive slightly later than expected because the twisted spacetime alters the light's path. If such effects are measurable around stars, could similar but subtler effects exist at the scale of the universe itself? Szigeti's models suggest that a rotating universe would alter how its expansion rate evolves over time. In graphs comparing different scenarios, their rotating models predict a higher current expansion rate, one that aligns much more closely with the 74 km/s MPC value from nearby galaxies. In other words, if the universe spins just right, the numbers fit. And just right means once every 500 billion years. That's slow, imperceptibly so, but it's also right at the edge of what their model allows before physics breaks down entirely. The coincidence is striking. The rotation required to solve the Hubble tension is almost exactly the maximum rotation that the model permits without collapsing into causality-violating madness. Scenarios where time loops back on itself and logic fails. Could this be a clue? Or just an artifact of tuning a model to fit a preferred answer? That's the critical point. This model is not built from fundamental physics. It doesn't fully account for gravity, dark energy, or the complex behavior of matter and radiation in the universe. It's a simplified, idealized toy model, and it only works because the authors assumed it could in the first place. This is what scientists call fine-tuning, a solution that fits the data, but only because it was crafted specifically to do so. To make this more than speculation, observational proof is required. Ideally, one would detect the rotation directly. Watch galaxies shift slightly across the sky over decades or centuries, evidence of a grand cosmic spin. But at the predicted rate, such movement would be so small that it falls far below the resolution of even our most advanced telescopes. It's not just difficult, it's impossible for now. So the next option is to search for indirect clues. For example, if the universe were spinning, the clouds of gas that form galaxies might preferentially spin in the same direction, leading to an imbalance in the orientation of galaxy rotations. But the Galaxy Zoo project, which enlisted thousands of volunteers to classify galaxies, already tested this idea. In 2008, their analysis showed no significant preference. Galaxies spin left and right in equal measure. Another possibility, a spinning universe might not look the same in every direction. That would violate isotropy, one of the foundational assumptions of modern cosmology. But observations suggest the universe is both isotropic and homogeneous, uniform across all directions and locations. This consistency forms the backbone of the Copernican principle, the idea that Earth and its surroundings are not in a special or privileged position. Still, one curious observation remains: the so-called axis of evil in the cosmic microwave background. Some studies claim this ancient light reveals a preferred direction in the universe. It's a controversial idea, and many scientists suspect it's an observational artifact, possibly linked to the orientation of our own solar system. But if it were real, it could hint at a large-scale rotation. The jury is still out. So where does that leave us? At present, the idea that the universe spins remains fascinating, elegant, and unsupported by data. Szigeti's model is clever, but not yet compelling. To move forward, cosmologists need more than creative hypotheses. They need new observational techniques, more sensitive instruments, and above all, a more realistic mathematical model that can account for the known complexities of our universe. In the end, this is how science progresses, not in sudden leaps, but in bold questions, patient refinement, and a relentless search for truth. Whether the universe spins or not may remain an open question for years to come. But even in the act of asking, something valuable is gained. A deeper curiosity, a sharper model, a renewed commitment to look further, measure more precisely, and never stop wondering what might lie just beyond what we know.